Wow, that sucks. Okay, let's see. What is with that? That thing can't see a thing. All right, let's try that. All right, so Balmer thermometer. So in general, remember that it's the star's temperature that determines its spectral type, and the spectral type comes from the strength of its spectral lines. Hydrogen spectral lines are an important set that are used to classify stars. So we use hydrogen as an example of the kind of how it is that how strong lines are depends on the star's temperature. Because you might at first think that the fact that some stars have stronger, darker hydrogen lines than others would be due to them having more hydrogen, but that's not it. It's really the temperature that determines that, not so much how much hydrogen there is. All stars have about the same fraction of hydrogen in them. So the idea is the lines that are visible to the human eye are the Balmer series lines, where the electron has to start on the n equals 2 level in order to absorb those photons. And so in order to get strong Balmer series lines, you need to have a lot of hydrogen atoms with the electron in the n equals 2 level. Because if it's in any other level, it won't be producing Balmer series lines that are visible to the human eye and to other instruments that work in the same range of wavelengths that our eyes do. So it's a story of Goldilocks and the three stars. Goldilocks wanted to have stars with strong hydrogen lines. So first Goldilocks looked at a very cool star, and it turned out that star was too cool for strong hydrogen lines. Why? Because while one way to get electrons up to higher energy levels is by having them absorb photons, another way is by collisions with other atoms and with electrons and so forth. And if you have a star with a temperature a lot less than about 10,000 Kelvin, the atoms in the star are not moving fast enough for the collisions to have enough energy, typically, to excite atoms out of the ground state. If you just let a bunch of hydrogen atoms alone, the electrons will all end up in the ground state. And in a cool star, almost all the atoms are in the ground state because the collisions aren't strong enough to kick electrons up into higher energy levels. And if virtually all of your atoms are having their electrons in the ground state, can you produce Balmer series lines which need electrons in n equals 2? No, you cannot. So in cool stars, we have weak spectral lines because most of the atoms are in the ground state, n equals 1, where you don't make Balmer lines from such atoms. Meanwhile, if you have very hot stars, the atoms are moving so fast, the collisions are so violent, that they strip the electrons off the atoms. The electrons are liberated from the atoms, and what is that called? Ionization. Oh, very good, yes. So, in very hot stars, most of the hydrogen atoms are ionized. They just don't even have an electron anymore. They're not even atoms anymore. They're just protons floating around, having lost their electrons. And so very hot stars don't produce very strong hydrogen lines because most of the atoms, most of the hydrogen is ionized already. But at a kind of medium temperature for these purposes of 10,000 Kelvin, it's hot enough that collisions have produced a fair population of atoms with electrons in n equals 2, but not so hot that you've ionized them all. In other words, in Goldilocks terminology, 10,000 Kelvin is just right. A significant number of hydrogen atoms remain neutral, not ionized, but are also excited to n equals 2, able to form Balmer absorption lines. So that's like the Balmer thermometer in terms of how strong the hydrogen lines are, depends on the star's temperature. That's what it comes down to. And similar kinds of arguments can be made for other elements. So all the elements have the strengths of their lines being dependent on the star's temperature. But different temperatures are ideal for different elements, which is why the different spectral classes have different looking spectra, because stars of different temperatures are, different elements have different ideal temperatures for forming their spectral lines, and so stars of different temperatures have different spectral lines which are stronger than the other ones, is what it comes down to. Yes?
Is 10,000 Kelvin like the universal number, or just for hydrogen?
It's just for hydrogen. That's the idea. It's just for hydrogen. For calcium, a cooler temperature is better than that. So the sun has strong lines of ionized calcium because the sun's temperature is nearly ideal for the formation of ionized calcium lines. Calcium, when it's ionized, still has some electrons left, and so that's why it still has spectral lines, because I'm talking about calcium, which has only lost one electron, but calcium has a lot of electrons in it, unlike hydrogen, which only has one. So the sun is nearly ideal in temperature for forming calcium lines, but not so great for forming hydrogen lines. So the sun has strong calcium lines, not such strong hydrogen lines. A star like Vega is close to 10,000 Kelvin, ideal for forming hydrogen lines, not so great for forming calcium lines. So a star like Vega has strong hydrogen lines, not so strong calcium lines, and so forth. We do that for all the elements. Yes?
I get that it's not warm enough, that star less than 10,000.
Yep.
But what about absorbing photons? Is that not like, because it's at the
Yeah, so two things. It can certainly absorb photons, but they won't be Balmer series photons.
Because it's at the ground level?
Because it's in the ground level. So the photons it absorbs would be Lyman series photons, rather than Balmer series photons. Note the Lyman series is in the ultraviolet. The other thing is, a star that cool doesn't have a whole lot of ultraviolet light that it emits, so actually even the Lyman lines aren't going to be so strong because there is not that much ultraviolet light being given off by the star if it's way less than 10,000 Kelvin. But a star that was cool like that would be better at making Lyman series lines than it would be at making Balmer series lines. Because the Lyman series is what you get from n equals 1 electrons. Good question. Okay. I forget, like, was this your question? And yeah, no, okay, so then you had a question, right? Yes. So, but first, anybody want to add any more to this? Yes?
Is this just a way for us to see is this a way to show how hydrogen absorption lines are seen in, like, the spectrum? Or is that what
It's that, and it's more than that, in that, so remember there's the spectral classification system, O, B, A, F, G, K, M, based on the strengths of the star spectral lines. And hydrogen is a good example of a set of spectral lines that we use when we're classifying stars. So we're using it as an example of why it is that an element's spectral lines will be strongest at some certain temperature that's ideal and weaker at other temperatures. We've used hydrogen as an example. Other elements have different ideal temperatures because they have different energy levels. So we use hydrogen just as an example, is what it comes down to. And because hydrogen is far and away the most abundant element in stars, so it's a good example for that reason. Because astronomers at first thought that stars with weak hydrogen lines don't have much hydrogen in them. However, Cecilia Payne came along and said, no, actually every star is made mostly of hydrogen. Stars which have weak hydrogen spectral lines have weak lines because the temperature's not right, not because they don't have a lot of hydrogen. They all have a lot of hydrogen. Yes, question?
The equation for the solar parallax, are we going to have to, is it just looking more like no equation?
You should be able to use that. You should know that D is 1 over P. I mean, I give you the formula, so you know D is 1 over P. But you should be able to apply that. If you know what the star's parallax is, you should be able to figure out its distance. So if its parallax was half an arc second, how far away is the star? D is 1 over P. The parallax is 0.5 arc seconds. How far away is the star? 2 parsecs, right? 1 divided by the parallax. In particular, remember that we did a lecture tutorial about parallax, and so you were asked to find a moving star, and how much did it shift back and forth, and based on that, what's its parallax, and how far is the way a star? I want you to be able to do something like that, potentially. Yep. Yes?
What other math questions?
Well, it could be anything that is, basically anything would be based on something that you saw in the Mastering Astronomy formula. I give you the formulas, you need to know how to use them.
The constants do like.
Yeah, I give you the constants, yeah, right. No, I don't expect you to memorize all the constants. I mean, you should know the speed of light is 2.9979245 times 10 to the 8 meters per second, but I'll give it to you anyway. No problem. It's easier to remember 3 times 10 to the 8 meters per second. But it's yes?
On the luminosity equation, will you give us sigma and T? Like, will you give us flux?
You mean, will I tell you F equals sigma T to the 4th? Is that what you mean? Like, will I give you the formula?
Will you give us the values? Like, I don't
Yeah, like of sigma, for example?
Yeah.
Yeah. All those constants like that. Well, T is something you might be asked to solve for, or you might be told, and then, you might be told the temperature is 6,000 Kelvin, what's the flux? Or the flux is something, what's the temperature? Yeah, right. Yeah. But I'll give you constants like the sigma, stuff like that. But T is something that is something you might want to find, or to use something. Soon I'm going to get out my pins and go like that, and somebody asks a question. No, we're going to get that chicken part of the We'll go over black bodies, like just in general, or yeah. So black body is an ideal emitter and absorber of radiation. What fraction of the radiation falling on a black body does it absorb? 100%. So the name black body comes from how they would look if the temperature was low enough that they were not emitting visible light. They would look as black can be. In other words, you'd be getting no light whatsoever from them, and so they would be, you wouldn't see any details in them or anything like that. It's not a very good name though, because if you heat it up high enough in temperature, it starts to glow, and so as the temperature increases, what happens to how bright the black body is? It increases, right? And it depends on the temperature. So what power? F equals sigma T to the what power? To the 4th power, right? So if I double the temperature of a black body, what happens to the flux? It goes up by what factor?
4?
Not 4. It goes like the temperature to the 4th power. So if the temperature goes up by a factor of 2, the flux goes up by a factor of 2 to the 4th power. Whatever you do to the temperature, whatever factor you increase the temperature by, the flux is increased by that factor to the 4th power. So if I double the temperature goes up by a factor of 2, the flux goes up by a factor of 2 to the 4th. What's 2 to the 4th power? No, that's 2 to the 3rd. 2 times 2 is 4, times 2 is 8, times 2 is 16. So it'd be up by a factor of 16 in that case. If I made the temperature 10 times bigger, it'd be brighter by a factor of 10 to the 4th power, 10,000 times brighter. And so what happens to the color? As the temperature increases, the wavelength of maximum emission, the brightest wavelength that it emits, what happens to that? Does it get longer or shorter? Shorter, yep, shorter. So 2 stars, Betelgeuse and Rigel. Betelgeuse is red, Rigel's blue. Which one is hotter? Rigel. The blue one is hotter, right? Artistically, we use red and yellow and orange as warm colors, and green and blue as cool colors. Scientifically, that is totally backwards. Red, orange, and yellow are cool colors, and blue and violet are hot colors, scientifically. However, flames tend to be orange and red, and so that's why we associate them with warmth. But really, a blue flame would be hotter than a red flame. That's if it's not getting its color from speckle lines. Yes?
You're thinking about luminosity and brightness of stars. The difference being that luminosity has to do with actual power or energy that the star gives off.
Yeah, power is actually the right word. How much energy per second the star's giving off? That's the power.
Whereas the apparent brightness would be how we perceive it.
Yeah, so in terms of, yeah, you're right. So the definition of brightness is how much energy per second we get per unit area on our detector. Energy per second per square meter. But in terms of the explain it to a kid kind of thing, you know, like I'm trying to explain to a kid, what's the difference between luminosity and brightness? Well, if I go to a 5-year-old, well, the luminosity is the total energy per second, and the brightness is the energy per second per square meter, they'd be like, thanks, right? Or not even that, be like, mommy, or something like that. But on the other hand, luminosity is kind of, in a sense, how bright the star really is, and the apparent brightness is how bright it looks to us, in kind of a rough speaking. Luminosity is how much energy the star is actually giving off every second as a whole. Brightness is what we see here on Earth. So if 2 stars have the same luminosity, they won't necessarily appear the same brightness, because if one's further away, it won't look as bright, even though they have the same luminosity. Yes?
So how, is the setup the same as last year?
Yeah, setup of the exam is very similar to last time. Yeah, so a bunch of multiple choice questions, some short answer questions, some essays/problem questions.
Okay. So for most of the math, or at least the one that I think was, that is like the luminosity.
There's the luminosity. There is like, you know, Stefan Boltzmann law kind of stuff. Like there's the parallax is in there. Basically, if you look over the problems from the mastery of astronomy, that's the candidates for being a problem on the exam, or at least something very similar to that. There will be different numbers being a problem on the exam.
So we're going to get the equations?
Yeah, I'll give you the equations in the form of an equation sheet at the end, so you know your job is to recognize which equation is appropriate to the problem at hand and that sort of thing. Yeah. And thus begins the master quiz. Who's going to stand up first? I'm going to give everyone else permission to start standing up. What's that? Yeah, right. Unless you leave at the beginning because you thought it sucked. Right, yeah. You're welcome. What's that? Yeah, right. Yeah.
Who's prepping for the bars?
Why do you have so much ketchup?